Okay, so welcome to this video that's going to talk about linear programming. And in this video, we are going to stick to the basic definitions and examples of linear program. So we are not going to get into solving anything. Our goal is to understand what linear programming is. Excellent. What is linear programming? Linear programming is a kind of an optimization problem. It's a very important example of an optimization problem. The world of optimization consists of a large variety of problems which are useful, and linear programs are a small but important part of optimization. And the short form of a linear program is LP. We are going to use this throughout this class, and so I would like you to get used to calling these things LPs and understanding what I mean when I talk about an LP right from the get-go. All right, so without much further ado, let me just talk about linear programs. What are they? And define them more formally in the next slide. So in this slide, we have an example. And in this example, we have four variables, x1, x2, x3, and x4. And these variables are our unknowns, okay, for which we need to find suitable values. And we are going to call these our decision variables. Great. So the decision variables are defined, x1, x2, x3, x4, and our goal is to find values for them. The goal is also to maximize this objective function 2x1 plus 3x2 minus x3 plus x4. And because it's a linear program, the objective is a linear function. Okay? So what does a linear function mean? So informally, a linear function is something which cannot involve terms like x1 squared or sine x1 or e to the x1. So you cannot have these kinds of things. But what can you have? Well, you can have variable times constant. Okay, and that's a term. A term can be a constant. And you can make up a linear function by adding up these kinds of terms. So every term can just be a constant times a variable, and in this case the constant is 1 minus 1 times x3, and you sum up some of these terms and you get a linear function. So hopefully everyone knows what a linear function is, and if you didn't know about it mathematically, the definition is right here. It's a variable times a constant, or a constant and a sum of these kinds of terms becomes a linear function. Okay, let's keep that in mind. And we maximize subject to some constraints. And the constraints are linear inequalities. Okay, linear inequalities. Or they can also be equalities, linear equalities. Okay, and each inequality has a linear left-hand side and a constant right-hand side. Okay. And you can also have greater than equal to, and the equalities have a linear left-hand side and a constant right-hand side, but you have an equal to. All right, so Shalom in his lecture is going to tell you how to convert all of these kinds of linear programs into a single and convenient standard form, but we are going to ignore that kind of a consideration just yet and simply define what a linear program is. To summarize, a linear program is to maximize, and it can also be minimized, and again Shalom will address this issue. We'll also address this in the next lecture. You can either maximize or minimize a linear objective function subject to linear constraints. So in this slide, we are making that much more formal. So we have decision variables x1 through xn in this slide. So those are our decision variables. We are maximizing a linear function, c1x1 plus c2x2 plus cnxn. So we are maximizing a linear function. c1, c2 through cn are constants, constant coefficients. Okay, these are constant objective coefficients, so we are maximizing that. We can also minimize that, but again, Shalom will address this converting minimization to maximization, and it's really trivial, so we'll leave that alone. And you can have linear left-hand sides, constant right-hand sides, and I have written less than equal to for these constraints, but it can also be a less than equal to, a greater than equal to, or an equal to, and Shalom will show why it suffices to just consider less than or equal to. Okay, so that's the general form of a linear program. It's the optimization of a linear objective subject to linear constraints. All right, very good. Okay, let's look at an example of a linear programming problem right here. So this is an example of a linear programming problem. Its decision variables are x1 and x2. The objective function is x1 plus 2x2, 1 times x1 plus twice x2. That's the objective function. Our goal is to maximize this objective function. The inequalities are minus 3x1 plus x2 less than equal to 2, x2 less than equal to 11, x1 minus x2 less than equal to 3, x1 less than equal to 6, and this says x1 greater than equal to 0 and x2 greater than equal to 0. And implicitly the constraints are all conjoined together, and there's a big and that goes between every constraint. So it needs to satisfy this and this and this and this and these. Okay, what kind of an answer am I looking for from a linear program? Because it's very important to know these things and get these things clear right away. Okay, so the kind of answer I'm looking for is a solution like x1 equals 6 and x2 equals 11, and the optimal objective value is the value of x1 plus 2x2, which is 6 plus twice 11, which is 28. So we need a solution, an answer like this, and the solver looks at this problem description and comes up with this answer. So let's try and understand what this answer means. To first understand that, we need to first look at the feasible region of the linear program. Okay, and the feasible region is, if you forget about the objective for a minute and just look at the constraints. Okay, so let's do that. Just look at the constraints for a second. Okay, let's get rid of all the writing on the slide and look at the constraints. All right, so if we do that, these are the constraints right here. Let's look at all the values of x1 and x2 that satisfy these constraints without worrying about the objective function. So we'll forget about the objective function just for a second and look at all the values of x1 and x2 that satisfy these constraints. So those values have to satisfy minus 3x1 plus x2 less than equal to 2. And geometrically, if you look at it, it's this straight line. So this straight line is minus 3x1 plus x2 equals 2. And everything to this side of the straight line is less than equal to 2. Okay, and likewise x2 less than equal to 11 gives rise to this straight line. Okay, the straight line itself is x2 equals 11, and everything below the straight line is x2 less than equal to 11. Okay, and if you keep going, you see that every side, every constraint gives rise to a side, and together you get a figure that forms the feasible region. And in this case, the feasible region is called a polygon. It's a two-dimensional polygon. In general, we'll call it a polyhedron, and we'll talk about that in the very next video. Okay, so if that part is clear, then let's look at what does it mean for the linear program to be solved. Okay, so we've started by defining an example of a linear program, and we have looked at how the constraints together give rise to a feasible region. Okay, now if that's clear, then let's look at what's the meaning of this objective. All right, the meaning of this objective is very simple. We have x1 plus 2x2, and we can look at all the points for which x1 plus 2x2 equals 0. Okay, and that forms the straight line. We can look at all the points for which x1 plus 2x2 is 35. That forms the straight line, and so on and so forth. So if you want to say x1 plus 2x2 equals some c, you get a parallel family of straight lines like this for various values of c. As c increases, you go in this direction, and as c decreases, you go in this direction. The goal of a linear programming problem is to find a point x1 comma x2 inside the feasible region, inside the green region, okay, so that this function x1 plus 2x2 is maximized. Okay, let's take examples. Let's take 0, 0. 0, 0 gives you 0 plus 2 times 0, which is 0. So the objective value achieved here is 0. But if you look at this point, 0, 2, this achieves an objective value of 4. Okay, so obviously 0, 2 is better than 0, 0. This is much better than 0, 0 because the point 0, 2, which satisfies all the constraints, achieves an objective value of 4, whereas 0, 0 only achieves an objective value of 0. And we are interested in maximizing x1 plus 2x2. If that's clear, let's also look at 311. How does 311 fare? Well, 311 achieves an objective value of 3 plus 22, which is 25. Okay, this is even better than the value of 4 that was achieved by 0, 2. So 311 is even better. And likewise, if you look at 6, 3, then this achieves an objective value of 6 plus 2 times 3. Okay, that's 15. And that's slightly worse. So it's in the between 0, 2 and 311. And since we are maximizing the objective, we prefer 311. So we can keep playing this game, but there are infinitely many points here. I mean, it's not a finitely many points, so there's infinitely many points. So how do we find the optimal answer? And in this case, it's just staring at us, because all we do is we look at where does the straight line of x1 plus 2x2 touch the region, so that if you move the straight line ever so slightly, it no longer touches the region, right? So in this case, you get x1 plus 2x2 equals 28, just touches the tip of this region, and if you try and increase it ever so slightly, it no longer does. And immediately you conclude 6, 11 is the best value you can get, and it gets you a value of 28. Okay? So the idea behind a linear programming problem is to find that value of x1, x2 inside the green region that maximizes x1 plus 2x2. Excellent. If that's understood, then we are in a great shape throughout this entire semester. Okay, so what are we going to do about linear programs? So first, let's visualize it. Let's understand what linear programs look like and what does solving a linear programming problem mean. We got some idea of that in this lecture. I'm going to give you more ideas in the next lecture. And then we are also going to talk about some broad overviews of algorithms for linear programming, like the simplex method, the ellipsoidal method, the interior point method. Just get you acquainted with the landscape a little bit better before we go ahead and start solving some problems. Okay, so that's going to be the purpose of this segment, and we are going to start in the very next video to look at what do linear programs look like. Let's do some more details, and what does solving a linear programming problem mean. And once these two concepts have sunk in, we are in a good shape to start considering algorithms for linear programs. Thank you, and I will see you in the next video.